let me introduce our speaker tonight. So I want to thank Ken Wyatt for being here. Ken, WA6TTY, the owner, principal of Wyatt Technical Services. He is the past senior technical editor of Interference Technology magazine. And if that isn't appropriate to the topic tonight, I don't know what would be. So, Ken, I'm going to let you take it away. Thanks very much for being here from a hotel room in Austin, Texas. The floor is yours. And you're on mute.
There we go. So am I still sharing or not? No, I guess I'm not. Hang on. Oh, okay. Yeah, so it's nice to see so many faces I recognize, and really thank Bob Whitty and Lauren for inviting me. I have given this talk to the Mountain Amateur Radio Club, which I'm a member of, and I also gave it, as you can see on the bottom, last year to one of the IEEE symposiums on EMC. So, and then I think I gave it to a club on the West Coast in the Bay Area. So it's been an interesting topic, I think, to a lot of amateurs. And if you have noticed that the background noise has increased over the last 10 to 20 years, you're not alone. And that's really what I'm going to be talking about tonight. So briefly, just a little bit about myself. I was licensed in 1973 as WA6TTY, and I was in college at the time. My career started in aerospace as a microwave engineer. Did that, in fact, microwaves, and then I switched companies and started designing DC to DC converters for various missile projects. And then I moved over to Hewlett Packard and later Agilent Technologies as their EMC engineer. And I was very fortunate to be working directly with Bob Whitty on one of his very first projects as a project manager. I left Agilent in 2008 and have been consulting in electromagnetic compatibility since then. I've written a number of articles and books, and the latest books, or the last three on the list there, is EMC Troubleshooting Trilogy, I call it. And it's comprised of 3 different volumes, all available on Amazon. So with that, let's launch into the presentation. So I call it urban RFI, and we have a lot of sources, which I'll talk about, that have increased the noise floor, basically. It's certainly an issue for HF operators, and even can extend up into the VHF frequencies. It doesn't affect FM too much because of the capture effect, but certainly if you're working sideband or CW, it's going to be an issue. I've noticed the noise floor has increased over probably the last 25 years. So I've seen at my house an S7 to S9 urban noise level, depending on the bands. And I take my radio out to the middle of Utah, and it's S0, and it's so nice to operate then. So largely, it's from switch mode power supplies, lighting, various kitchen appliances, power supplies, and the little modular wall wart supplies, which I'll describe later. This RFI is real easy to see on the waterfall displays as regular spikes, basically. And we'll be talking about some mitigations as well. So generally, there's three dominant sources. There's impulse noise, and that's due to defective equipment in the mains, either arcing or corona or lightning. And that typically affects the bands up through 7 megahertz.
Ken, sorry to interrupt, but are you changing slides?
Yes.
They seem to be stuck on the second page of your slide.
Well, that's probably an internet thing. I'm not sure what I can say about that.
I wonder if you shared the wrong window.
Well, let me see. Oh, yeah, I think so.
I got
sorry about that
before.
Yeah, the little icons aren't very big when you call up the screen share. So let me. Okay, so we did the introduction, types of noise. Everybody see that okay now? Is that it? I see
Yeah.
Grace nodding.
Yep,
yes.
it's good.
Yep.
Okay, good. So I'll continue, sorry. So we talked about impulse noise, and that's things like lightning, just sporadic things happening. And then the electronically generated noise, which is really what's dominant now, has to do with digital bus noise, variable frequency motor drives, which is becoming an issue, switch mode power supplies, solar controllers, wall warts, and LED or CFL lighting. And if you've purchased any new kitchen appliances, that's becoming a major issue. Then the signal leakage is really minor. That's like VDSL modem or cable TV interference coming in on 2 meters. So we're going to get a little technical, but I think there will be something for everyone. Oops, got to watch what I do with my fingers. I think there will be something for everyone in this talk. So this is a generalized digital signal waveform, and the point here is that the key contributor to RFI or high frequency harmonic emissions is primarily due to the rise and fall times of the digital signal as it's going from a low to a high and then back to a low. And you can see in the picture on the middle there, the 20 nanosecond rise and fall times. Let me just a sec. The 20 nanosecond, you can see it's a relatively slow rise and fall time, and you've got some harmonic content at the bottom there. And the on the right side, it's a 5 nanosecond, a lot faster rise and fall times. You can see that the harmonic content is a lot more and higher. Typical digital product, this is what it looks like if you're looking from 10 megahertz to 1.5 gigahertz, which covers the cellular and GPS bands, which is circled there. You can see two kinds of noise. There's what we call narrowband in the aqua trace. That's an Ethernet clock. And then the purple trace is kind of a broadband rise in the noise floor. basically is what it looks like. And that's typical from a DC to DC converter, these onboard DC to DC converters. And this noise can not only affect your HF, which is in the lower third of that screen, but cellular and GPS as well. Now here's an example of 60 hertz power line noise. And this I pulled off from QST September 2021 on an article on RFI. And you can see that the 60 hertz sine wave crosses 0 twice per cycle. So you get 120 hertz noise or harmonics. This is a block diagram of a DC to DC converter, and you can see on the left the AC input coming in to a high frequency switch, to a power transformer, and then the filter, output filter. And it's this switch, switching up and down on the transformer primary that can really cause a lot of EMI. The bottom figure is a typical onboard DC to DC converter, and a lot of digital products have 3 or more of these converters operating between 1 and 3 megahertz. And so you get this broadband noise happening. Now, if you look at some of the waveforms on these switch mode power supplies, very often you see ringing. And I've circled a couple there, a couple examples. Just note that ringing. And what happens is that ring frequency, which I'm showing on the left there, if you translate that to the frequency domain, that ring frequency will actually cause a broad peaking in the emissions. And here's an example where I'm measuring some ringing on a small DC to DC converter. And here's the result. So you see the ringing on the left, and it's ringing at 217 megahertz. And you can see in the aqua, the ring frequency, and in the purple, the second harmonic of that ring frequency. And you can even see higher harmonics than that. So we're looking out to a gigahertz here, and you can see all this broad band spectrum that is potentially going to interfere. Now, we probably all know that the cheap wall wart power supplies are probably not the quietest around. I took one apart, and it has no power line filtering whatsoever. And you can see the result as I measure that. And we're looking from 150 kilohertz to 30 megahertz. So basically the HF band. And you can see it's pretty nasty. I just tacked on a conventional power line filter, and you can see the results on the right. And it's quieted way down. But this wall wart is up to 70 dB over the FCC Class B limit for household appliances. And of course, you'll definitely hear that in your receiver. I measured a typical DC to DC converter, one you would find on a digital board. And you can see that here you can see that there's something called differential mode in the violet and common mode in the aqua. And again, we're looking from, well, in this case, 10 kilohertz to 30 megahertz. So basically the HF band. Now I'm going to measure some things like light bulbs coming up shortly. I ended up with a whole bunch of Apple power modules, and several of these were counterfeit. And I thought, I'm going to measure each one and compare them. So I mean, they look they're labeled and have the same regulatory labels and so forth as the real ones, but they really differ in performance. The real Apple ones are largely under the FCC Class B limit. But look on the right-hand side, the counterfeit Apple power modules. They don't have very much filtering, and so stick with Apple. In fact, I measured other brand name manufacturers like Belkin. Belkins were good also. So if it's a well-known brand, it's probably okay. But I would not get the unbranded ones. Now I measured my Powerline noise. This is at the house, and I'm looking from 100 kilohertz to 100 megahertz. So you can see the HF band is labeled there. And my Powerline's pretty noisy. So I was experimenting with a couple ways to filter that Powerline noise. One way in blue was with an isolation transformer, and in green was a special purpose filter by a company called On Filter. And you can see in the green, the yellow is the baseline noise floor, and that On filter was virtually quiet almost all the way through the HF band. So here's some interesting tests I ran about 10 years ago. I purchased, I think this was in 2010, I purchased some of the very first LED light bulbs, and I ran them in a standard EMC test for conducted emissions. And that's the setup, and you can see on the spectrum analyzer the results of that particular bulb. And I'm looking from 150 kilohertz to 30 megahertz. Here's the results, what I call the good, the bad, and the ugly. And so this is back in 2010 vintage. On the left is a Cree model bulb. In the middle is a Philips. And on the right is a Utilitech, which is, I think, Home Depot labeled bulb. And again, the yellow is the noise floor, and the purple and aqua are the conducted emissions. Now, I repeated the test just last year on a couple bulbs. The Philips, I bought both these at City Market, which is a Kroger store. So the Philips on the left was not bad, but what surprised me was the Kroger brand Everyday Living bulb. And you can see that its emissions are hardly out of the noise floor. So I guess I recommend King Super or City Market Everyday Living bulbs if you're operating HF. So that was a surprise. Now we're going to get back to HF receiving and what to do about it. There's three useful mixes of ferrite, 31, 43, and 75, and I've got a plot of each one of those coming up. A lot of us try using the clamp-on ferrites, and they don't really work that well at HF. The toroid cores work way better, so that's something to keep in mind. Of course, powdered iron is not really designed for, it's designed for RF power transfer, not for filtering. So you don't want to use those. The Q is too high. We'll talk about commercial line filters, and a topic that you may not be that familiar with is filtering the transmission line and antenna. So back to Ferrite. Ferrite actually has a page on their website called Smart Home, and they have recommended various kinds of ferrites for various applications. So you might go to the ferrite.com website and check that out. But we're going to talk about commercial line filters, and one of the things you need to be aware of is to connect these properly for best filtering. You need to bond the metal case back to your chassis of the radio or a power supply, whatever you're trying to filter. If you don't bond that case down, it's not going to filter the common mode, which is what's particularly nasty. A friend of mine, Dave Eckhart, W0LEV, recently purchased a new refrigerator. And the refrigerators have these variable frequency motors on them now, which basically is a switch mode controlled motor. And so you can imagine the energy, the harmonic energy that comes out of these appliances. Now he's an amateur radio astronomy kind of guy, so he's got to have a really RF quiet location. So what he did was take a number 75 material toroid and wrapped the power lines, all three of them, the line, neutral, and safety ground, 3 times around the core, and that was enough to really knock down the RFI from the refrigerator. So there's pictures of how he did that. Now, I mentioned filtering the antenna. It turns out that your antenna coax run from the antenna back to the radio can be quite an effective antenna itself for picking up this urban RFI. And so it turns out you can use the same kind of a common mode choke that you would use, say, filtering the power line on a power supply, and you can put it in series with your feed line. And Dave, W0LEV, did some experiments, and you can see a lot of his toroids that he's wound. You wind them bifilar, and on one winding, you put that in series with the center conductor of your coax. The other winding connects the 2 shields. And you can see in the middle, there's a chart of impedance versus frequency for the different materials. You can see 75 material is good stuff to use for HF. Some people use 31 material or 43 material. But you can see where it's most effective there. So here's some experiments that he did on his IC 7300. Now he's using a 450-foot long doublet fed with parallel wire transmission line through an antenna tuner. So rather than coax, he's putting this common mode choke in series with the parallel line. So without the choke, he was measuring a level of S8.5. And you can see there's a lot of signals that are hidden in the waterfall display. Then he added a single common mode choke between the feed line and the radio, and the noise floor, the background noise floor went down to S5.5, and he calibrated his S meter for every S number. It's 3 dB on this particular receiver. So there was a 9 dB reduction in noise. You can see in the bottom display, there's a lot more signals visible. So this is a technique that you can try using. There's a company, kf7p.com, that makes these common mode chokes that you can put in your between the antenna feed line and the radio. You can also put them at the antenna. Now, a lot of antennas, that they have you coil up your coax into a loop of several turns, and that's supposed to work as a common mode choke. It actually doesn't work all that well. But if you put one of these at the antenna and at the radio, you can potentially get a lot quieter background noise. You can see this one in the picture. I measured the common mode impedance at different bands from 80 meters to 6 meters. And you can see that the common mode impedance is really high in the HF bands. It's over 1,000 megahertz or 1,000 ohms, and so that's what you want for common mode. For differential mode, of course, that's your signal. It's not going to affect it that much. So if you're really into HF, you want to try and minimize the RFI sources in your own home, and you can do that by turning off circuit breakers and so forth. There's the ARRL has good information on general RFI hunting, which I'm not going to go into that much. You want to avoid buying noisy power supplies to begin with, especially these days. And there's good brands that are especially quiet. I'd remove all your older LED bulbs and replace them with something quieter, and then avoid using unbranded wall warts. So we'll talk about spectrum analyzers and using shortwave radios and stuff to find RFI sources. But here's some good resources. Now, the RFI book from ARRL is, I have to believe it's under revision. They've been talking about doing that for some time, and it's no longer on their website. So hopefully they'll come out with the 4th edition. I also recommend the grounding and bonding. I'm not going to get into that topic, but it's maybe a topic for a whole another presentation. And then the little RFI pocket guide I wrote along with Michael Gruber is available. So my friend Dave was in the market for his first flat screen TV, and this was back when they had the plasma sets, and he bought one of those things, and it was so bad he actually had Panasonic buy it back from him because he's an EMC engineer too, so he measured the thing on the range, and it was way over the FCC limit. Panasonic bought it back. And so knowing that, when I was in the market for a flat screen, our first flat screen TV, we had a choice of plasma, or we had the choice of the newer LED backlit sets. And so I took my spectrum analyzer into Best Buy, and that's it there. Hooked up an antenna to it, and I started scanning all the sets on display, and it was soon. I was soon surrounded by a bunch of salespeople, wondering what I was doing, and so I had a chance to give a little EMC seminar right there. I did end up buying an LED screen because the plasmas were really, really bad. Can use portable AM or shortwave receivers to find noisy sources at your house. And these work nicely. And you can use things like the Yaesu FT817 or 818 to do the same thing, especially if you have Powerline noise. So I purchased one of these flag antennas. It's a kit that you can get from DX Engineering. It also comes with, or you need to get the little preamplifier for it because, as you can imagine, a small loop antenna that's good in the whole HF band is not very sensitive. So, but the neat thing about the flag antenna is that it has a null on it. And it's a relatively sharp null, and it's a lot more efficient in finding like Powerline, arcing, or corona. So there are some other mitigations you can do. You can operate in quiet areas like middle of Utah. SOTA and POTA is an option, where usually the noise floor is going to be a lot lower than normal. I already talked about my vacation experience in Utah with the S0 noise floor. That was pretty cool. And then maybe mobile operation. But I know it's tough operating HF at most homes, even in a rural area like I live in. The noise floor is pretty high. Future, probably not so rosy. Appliance manufacturers, believe it or not, are not regulated by the FCC, at least here in the US. They are regulated elsewhere in the world. So we're special here in the US. So you might bring shortwave radio, portable radio with you when you're shopping for kitchen appliances. There's an overwhelming number of cheap unfiltered switch mode power supplies and lighting and other power supplies, and it's just unfortunate. Something we're going to have to live with. I don't think the FCC's got any power to force that kind of change. So we hams, we're going to need to depend on our technical prowess. You might try filtering your antenna feed line, for example. And we may have to develop new technologies to battle this RFI pollution. I've got a bunch of references here, and hopefully you're recording this. If not, I can leave you the slides. But these are some pretty good articles. I would particularly recommend going to k9yc.com. He's got a lot of excellent RFI related articles. And he also sells the antenna chokes. Guess that's it, unless there's questions.
Ken, I'll start out with a question. It looked, or it sounds like that the bulk of the RFI that is within the home is going to be conducted. So the noise is getting placed on the mains, and it's being distributed around by the wiring in the house. Is that a fair assessment?
It is. So it is mostly conducted harmonic content, but then you connect that to wiring throughout your house, and it's going to radiate as well.
Do you get any benefit by putting, for example, when I had an opportunity to do a little bit of wiring in my shack, I put my radio equipment on one phase in the panel, and I put in all of the other electronics, a computer and power strips where there would be power supplies plugged in that weren't radio related onto the other phase. Do you get any benefit by going back to the panel before it's distributed back in? And would it be easier to filter if you could do it at the panel?
Well, a couple of good questions there. Yes, there is some isolation benefit for in connecting to different phases. And when we all used those intercom systems, do you remember those intercoms that you just plug it into the power line, and they would transmit a digital, I guess a digital signal in the wiring. Now this was like kilohertz, maybe 100 kilohertz kinds of frequencies, and you had to be sure to plug them into the right phase on your house, otherwise they wouldn't talk to each other. So I think there is some benefit. And as far as putting filters right at the panel, it would have to be a pretty big one to handle the current. But yeah, that would certainly filter anything outside coming in. The problem I think most homes have is you've got all the sources in your house already. And so, doing an inventory of the most noisy things and replacing them with something quieter would probably benefit you a lot. I was really surprised about the everyday living light bulb. I did not expect it to be filtered so well. And I bought a box of 4 of them, and I tried each one because I thought maybe there was a one-off one that was just better than the others, but they all measured very quiet. It's just amazing, especially compared to what I was able to purchase back in 2010, which were the first LED models that hit the market.
I have a question, Ken. So you mentioned we could go around the home with a little portable shortwave receiver. Is there a particular frequency that we would tune that receiver to kind of determine in the house what devices were the noisiest? Is there anything to look at?
Well, most switching power supplies are less than 3 megahertz these days. So 80 meters would be a good band to try.
Okay. Yeah, that's a pretty nice little tool that you mentioned there that we could kind of walk around and look at some devices, even appliances, and see what's going on. Yeah, thank you.
Well, and you want to, as you're getting closer and closer to the source, you might want to start increasing in frequency to zero in on it better.
Okay.
So what about photovoltaics and these big whole house systems where they have the inverters underneath each of the panels, and they can create quite a lot of noise. What is the best approach there?
A good question. So yeah, solar panels have started to become an issue, just because they're using unfiltered DC to DC power conversion, or poorly filtered. And I think companies like Solar Wind, I believe they do have an option for filtering, and it requires ferrites on the wiring of each panel, and then special DC to DC conversion with filtered converters. And I'm sure it's more expensive, and a lot of the installers don't know anything about RFI. So you, if you're going to specify one of these systems, you want to make sure that the company can provide a filter option. If they can't, then I would avoid that particular brand.
Ken, I had a couple of conversations with some installers recently, and you had in your presentation, which please do send me a copy of it so I can get it to Stephen to get it posted. But one of the references that you had in there was a 2016 article in QST that is excellent. And the interesting thing was I talked to 3 different solar installation companies. The first one, when I asked them, what do you do for RFI mitigation, was deer in the headlights. The second one was, we don't have any problem with that. All of our panels meet FCC specifications. So I automatically ruled them out. And then the third one said, gee, I have no idea, but let me check with our design guys. And they came back with a list of ferrite companies. But it turned out that they contacted their installers who said they didn't know anything about it and didn't want to touch it. So I struck out 0 for 3 on the 3 companies. But it's they know about it. Some of them do, the reputable ones do, and there are ferrite products available, and you can buy kits for it. But that article said that you can expect to pay 10% more for an installation if you do a proper RFI mitigation on it.
I can believe it. Now, there's an RFI email reflector that I can give you the email to. They've had a lot of discussions on solar panel RFI. Now, Ed Hare, W0TLM is participating in that discussion group, and it's interesting. Somebody will come on to send out an email to the reflector, and then there'll be, with some issue, and then there'll be a bunch of discussion afterwards, and so it might be something you might want to monitor for a while.
So, Ken, for those of us with already existing solar systems that are noisy, is it pretty much hopeless for us?
Well, I don't know. The first thing I do is start putting. You've got to identify where the sources are, and so you probably want to go up on the roof with a handheld shortwave radio or something, and try and figure out where the noise sources are. Once you've done that, then you can try applying some ferrite cores and wrap the power, the input and output wiring around those cores.
Yeah, but it's all under the panels. All the microinverters are under the panels, so it's a huge hassle. So, yeah, I've looked quite a bit into it. Yeah, I've got about an S6 or S7 noise level just from the solar panels, with everything else in the house turned off. So, yeah.
Well, I'd still try to put some cores on the wires coming out of the panels. That's probably better than nothing.
Yeah, that's a good idea. Thanks.
Yeah, Ken, from a history major here, I got a little solar panel, probably a 14 by 14 in my window, in my ham shack to trickle charge my 12-volt battery that I try to operate it off more than the inverter. Should I measure how much noise is coming off that little solar panel going into a power gate that charges the battery, and then utilize the IC 7300 goes into the power gate, and I just go off that 12 volt.
Are you getting RFI from that system?
Well, I operate on 100 watts and a wire strung through the trees. So I'm always got noise on there somewhere. But I'm not sure what I'm looking at when I'm looking at that waterfall screen. You know, if I turn the squelch down, yeah, I got nothing on there.
Well, you might try taking like a 31 mix or 75 mix toroid, which you can get from the K7.com. I can't remember his call letter. He sells cores, and try winding a few turns of cable around that core and see what happens. Can't hurt.
Roger that. Thanks.
LMR Engineering is another company to go look at. They've got quite a bit of information on their website. I'll put that in the chat.
I got one comment. You mentioned this, Ken, and I just want to amplify it. For a lot of this stuff, your circuit breaker panel is the place to start. Like I've wandered around with directional antennas trying to figure out where the noise is coming from. But if you can just twist yourself in knots, because as soon as it gets into if it's power line conducted, it gets into the wiring, you get all kinds of interesting patterns in your house. You can really get confused about what the source is. But if you go to the panel and go click, 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 and all of a sudden the noise drops, okay, it's on that circuit. And then you got to go find out what just turned off. And 90% of the time it's just one of those switching wall warts, or I've had a lot of problems with various routers, Ethernet, DSL, that kind of stuff. Those things are often pretty darn noisy. But anyway, you can narrow it down pretty fast if by flipping the breakers, assuming the device doesn't have a battery inside of it, which you also mentioned. But it's amazing what you can find just doing that.
That's a really good point to stress.
So Ken, how effective you showed a picture of your IC 7300 or your friend's IC 7300. When I look at my waterfall on 15 meters, I've got a series of spikes that go from top to bottom. And I haven't, because 15 meters hasn't been all that open until recently, I haven't paid a whole lot of attention to it. But how effective are the waterfalls on our receivers or on our SDRs that we have attached to our receivers for doing measurement if we don't have a spectrum analyzer?
Well, they're very helpful. If you take the difference between two adjacent spikes, that's going to be twice the switching frequency of whatever power supply or switcher is in the area. So for example, if something is switching at 10 kilohertz, you should get spikes every 5 kilohertz, every time it changes from a high to a low back to a low. So you take the difference that you see on the spectrum, and that's going to be twice whatever the switching frequency is, or the period of the switch. So it'll give you a clue as to whether it's most power supplies are going to line operated power supplies are going to switch like 100 or 150 kilohertz. So it's going to produce harmonics at twice that.
So I guess if you turn something off at the panel and they go away, that's a pretty good clue that you found
that is
circuit that it's on.
It's a little harder when it comes from your neighbor. So you've got to have that discussion.
So conducted is so even from a neighbor it can be conducted if you don't have one of the neighborhood transformers, if you're on the same transformer.
Well, it can be conducted if you're on the same transformer, but it's more likely going to be radiated from his home wiring. You've got this conducted current, high frequency currents flowing in your mains cable, mains wiring, and because the wiring is so long compared to a wavelength at these frequencies, it's going to be a very efficient antenna as well. So you really get both conducted and radiated, at least in the HF bands. Well, appreciate your questions.
Any more questions? And we'll release Ken. He's an hour ahead of us. It's almost 10 o'clock where he is. So.
Getting late. That's all right. So it's good to chat with you guys. Thanks again for the invitation, and appreciate that. If you have any questions, feel free to contact me through my website, emc-seminars.com.
Well, thank you very much, Ken.
Thank you.
Ken, great presentation. Thank you.
Thank you, Ken. Good to see you.
You all take care. I'm really impressed with your club and all the activities that you do. You guys are doing a great job.
Come down and join us when we're back in person sometime when you're in town.
I'd be happy to. Well, good night, everybody. Thanks again.
Good night. Thank you very much, Ken.